Okay, well, welcome back, everybody. Let me just start by pointing out, I think, Julia, thank you, put a link in the chat. So Sasha Kuznetsov is luckily out of prison, apparently, but some students from the Higher School of Economics are still in prison. And so Sasha asks that we devote our attention to trying to get them to be freed. And so I think, if I understand correctly, this was a new petition of the same thing on the same petition site that was started by Dennis Geitskory. I just signed that a couple minutes ago. I can maybe comment. I mean, this is quite a general problem throughout the planet, which is governments arresting people who are trying to demonstrate. Let's hope that problem goes away as soon as possible. Anyway, so to get back to the conference. So it's a great pleasure to introduce Colleen Robles, who will speak on completions of period maps.
Thank you, Carlos. And thank you to the organizers for the opportunity to participate. The talks have been great so far, and I'm looking forward to the rest. If you have questions, please just feel free to speak up. I'm not very good at keeping track of the chat. And I'm happy to stop at any point and explain something in greater detail. So this is joint work with Mark Green and Philip Griffiths, but it also builds on a project that was initiated with Radu Laza, and I'll say a little bit more about that later. The goal is the following. So what we hope to do is to use Hodge theory to apply, we hope to use Hodge theory to study moduli problems beyond the classical ones that you would have seen with, say, principally polarized abelian varieties or K3s. These all correspond to the case that the period domain is Hermitian, which is very special. And we are looking to extend some Hodge theoretic techniques to more general settings. And for us, that means that we're looking to extend period maps. So the basic setup is the following. I have some smooth projective variety, a normal crossing divisor, reduced, nothing fancy. And I'm looking at the complement, which is quasi-projective. And over that quasi-projective base, I have a period map. And I'm not assuming that D is Hermitian, and I'm not assuming that gamma is arithmetic. It might be thin. And I'm not going to try to compactify the period space over here. You may be familiar with the fact that in the classical case of a Hermitian D and arithmetic gamma, there do exist compactifications. We've already discussed some of them. These are the Satake, Baily, Borel, the toroidal compactifications, and in some cases, the intermediate semi-toroidal compactifications of Luenga. What I want to do instead is compactify the image of the period map. But it's also not enough to just compactify the image of the period map. If that was the only thing I wanted to do, then I would in fact be done by that recent work of Bakker, Brunarby, and Zimmerman when they show that the image of the period map is quasi-projective. I could just take the closure of the image. But I also want an extension of my original period map to the smooth projective completion. And that does not follow from the BBT construction. To get this extension, one needs to say something about what happens as the period maps degenerate across strata. And that's largely what I'll be occupied with describing today. Okay. So the goal is to get some version of this thing over here. So as a warm-up, let me remind you what the classical story is here. And today, when I say classical, I mean that D is Hermitian and gamma is arithmetic. So if this is the Satake, Baily, Borel compactification, then we know from the work of Borel that there always exists an extension. So we're basically done. The problem is solved, and the compactification would just be the image of B bar under the extended period map. Something that I'll come back to later is that if I look at a toroidal desingularization of the Satake, Baily, Borel, the existence of an extension here is a more subtle business. It may not exist at all. Okay. So the main result is the following. And I'm going to work with the Stein factorization of the period map. So here's the period map. I want to look at the Stein factorization. And the reason for this is that I'm going to use the infinitesimal period relation, the IPR, in a non-trivial way. And for that, I'm going to need to work with connected fibers. Okay. So the Stein factorization, I'm looking at this middle space, which is normal. It has finite fibers over the image of the period map, and then the map phi hat has connected fibers. Okay. So let's assume gamma is neat. We suspect this can be dropped, but I'm going to assume it for this talk. Then this image of the finite cover, this finite cover of the image of the period map is Zariski open in some compact Moishezon variety, which I'll denote with a T, phi hat T. So we suspect this is algebraic as an algebraic variety, but could we be reminded? So what neat means is that if I look at the eigenvalues of gamma, the only eigenvalue of norm 1 is corresponds to the identity map. Only the no, I need to say that again. The only eigenvalue of norm 1 is 1. I can say where that shows up a little bit later. It's basically so I can avoid dealing with some finite quotients. Okay.
Thank you.
And okay. And then in addition, this finite cover extends. So the finite cover extends to B bar. Okay. And that is a, I didn't write it down, but that is a, and is a morphism. Okay. In the category of algebraic spaces. So the basic idea of the proof is actually quite simple. And there's just one fiddly technical bit that we're going to spend some time talking about. So let me give you the outline for the argument. So what I'm going to do is look at an equivalence relation on B that's defined by the Stein factorization. So 2 points are equivalent, basically if they're in the same connected component of a phi fiber. This defines an equivalence relation on B. The image, I'm just going to call this hat image of the period map. So I don't keep saying hat and finite cover over and over, but keep in mind we're working with the Stein factorization. And the image of the period map is the quotient, and the period map itself is just the quotient map. Okay, so that's inside B. We need to work our way out to B bar. And for this, we have the result of Catani, Deline, and Kaplan on the algebraicity of Hodge loci. And this can be used to show that, that this equivalence relation is in fact quasi-projective in this sense. There's some algebraic subvariety, and I can recover the equivalence relation by intersecting it with B cross B. Now, suppose for the moment that in the larger space, X bar defines a proper holomorphic equivalence relation. If that's the case, then there's a result of Grauert that says the quotient has the structure of a complex analytic variety, and the quotient map is holomorphic. So all I need to do now is pass from the complex analytic category to that of algebraic spaces. And this follows from some results in a text by Ancona Tomasini, which says that as the as this PT is the quotient under an analytic map of a algebraic variety, it's necessarily Moishezon. And then Artin has some work from the early 70s, which shows that Serres-Gaga applies in this setting, and you can conclude that phi hat itself is a morphism. So I'd like to mention a couple of colleagues. It's Greg Perlstein, who mentioned to me a few years ago that thinking about equivalence relations was one way to approach the problem of constructing this extension. And Daniel Greb pointed out to me that, in fact, we do get this Moishezon structure recently. Okay, so this is the argument. What I have to do is deal with this red line. Okay. So I said that I had to show that X was a proper holomorphic equivalence relation. What that means is that for any point B in B bar, I need to find a neighborhood of that point with the following properties. I need for phi itself, where it's defined over that neighborhood, to be proper. So in particular, this means we're not going to get away with working in local coordinates at infinity in general. And I also need a proper holomorphic map whose Stein factorization over the full neighborhood is, well, I need a proper holomorphic map over the full neighborhood, and so that it agrees, the Stein factorizations agree where that makes sense. Okay, so let me describe to you where we're going to get these functions f to get this proper holomorphic map. So they're going to be built from the coefficients of a period matrix representation for phi, the period map. And before I describe exactly what I mean by that and go through an example, let me mention some implications. Because we're using more or less the entire period matrix, I'll make that precise, this gives the completion the interpretation of being a maximal Hodge theoretic completion, in the sense that it essentially encodes all the limiting mixed Hodge structure that's Hodge theoretically available from Schmidt's nilpotent orbit theorems at infinity. And it also gives it the flavor of a relative analog of a Kato-Usui toroidal construction. This is not a precise statement. I'm not making a strong claim here, but what I'm saying is that the compactification is more or less the sort of thing that you would expect to get if you had a Kato-Usui horizontal completion and you took the closure of the image of the period map in that space. Okay. So that means in particular that in the classical case, it looks a bit like what you would get if you were looking at the toroidal construction of Mumford. And so I mentioned that the extensions don't always exist to the toroidal compactification. So it's kind of striking that we actually get an extension in this case. And finally, the precise relationship to the toroidal constructions is a very interesting question. I'm not going to say a great deal about that. I'll make a couple comments as we go through the talk, but the answer is not obvious because the constructions are so different. Here we're constructing a completion by taking a quotient of a proper holomorphic equivalence relation, while Mumford defines boundary components and attaches them in a very subtle gluing process that involves fans. And we do not have fans here. Okay. So let me start to say a little bit about what I mean when I say that the period map has a matrix representation. And I'd like to start with the local picture. So first, I could just pick a point B where the period map is defined. Then we assume that it's locally liftable, which means that I can always find a neighborhood of that point over which the period map takes values in the lifted period map. There's a lifted period map to the period domain, and that gives us a period matrix representation. more generally, if I move out to a point at infinity, on the divisor at infinity, then Schmidt's nilpotent orbit theorem tells me that there's a local coordinate neighborhood around that point, so that phi has a period matrix representation in the punctured neighborhood. So let me discuss a little example to illustrate what I mean here. So let's just suppose we're looking at Hodge structures of weight 1 with Hodge numbers 2, 2. And so we have curves of genus 2, and you might imagine that we're pinching off a cycle to acquire a node, something like this. So if I go out to infinity, I might have a 2-parameter family, and my point B might lie where t is equal to 0. Then the period matrix can be represented. So think of these as the 2 column vectors that are spanning H10 or F1. This is the period matrix representation. For the most part, it's holomorphic. And in fact, those holomorphic functions extend to the full neighborhood. But we know from Schmidt that there is some singularity at infinity. And this is given by the nilpotent orbit. But if I subtract off log t, then what I'm left with does in fact extend to be holomorphic on u bar. So in particular, when I say that the function f is constructed from the entries of the period matrix, what I'm going to do is just take the holomorphic entries that are already well behaved. That's lambda and alpha. And then I'll take the exponential of the multi-valued period matrix entry to get a holomorphic map into, not into R3, into C3. Okay. So in particular, notice that there, because I'm working out at the boundary, there's a non-trivial monodromy action here. This is the log t that shows up. So when I say period matrix representation, it's possible that what I have is a multi-valued period matrix representation. Now, this is basically the picture that we're after, but the problem with this picture is that we're working over a local coordinate chart, so there's no reason at all that this map will be proper, and I need a proper map to apply Grauert's result. So the example I just went through is the right one to keep in mind if you're thinking about period matrix representations, but let me be a little more precise about what I mean for the general discussion. So the compact dual of the period domain is covered by Zariski open Schubert cells. And these Schubert cells are affine. In fact, they give us local coordinate charts on these homogeneous manifolds. And so one way to think about this is that if you restrict to a point inside the Schubert cell, it admits a matrix representation. It's just these coordinates in the CM. So in particular, if you go back to this example, the CM is C3. It's just the map that plucks out these three, these three coordinates. Okay. So that's for a fixed point. What does it mean for the period map to have a matrix representation over some subset of B? It means that I can find one of these Schubert cells inside the compact dual so that the monodromy over that set, not necessarily over B, but over that subset, will preserve the intersection of D with the Schubert cell. And the period map takes value in this quotient. So what that means then is that I can take these coordinates on the Schubert cell and I can pull them back to functions over the neighborhood, punctured neighborhood, curly O, but they may be multi-valued because I have this action of gamma prime. But that's something we'll have to deal with. But this is like having the log t in the local picture under the nilpotent orbit theorem. So the assertion that we have these period matrix representations is actually trivial in the classical case. If D is Hermitian, then there are several Schubert cells that contain D. These give you the bounded and unbounded realizations that show up in Baily-Borel's construction. In general, it's a non-trivial statement because the period domain will contain positive dimensional compact algebraic varieties. And so it cannot sit inside any Schubert cell because the Schubert cell is affine. Okay. So where do these period matrix representations come from? And I think the language that we've agreed on is that this is coming from what we're calling the global study of period mappings at infinity. And the way to think about it intuitively is that basically we want some analog of the sort of structural results you get out of Schmidt's nilpotent orbit theorem, but we want those results not over coordinate neighborhoods, but over larger sets where certain maps are proper. So try to make that precise. So let's look at the irreducible components of our normal crossing divisor at infinity. This is stratified by taking intersections. And I want to look at these smooth loci where I take one strata and I remove all the strata of lower dimension. So here, Z1 star would be Z1 minus the origin. So what does Schmidt tell us? He tells us that if I pick a point inside the base B and I let it move out to the normal crossing divisor at infinity, the period map, the Hodge structure parametrized by B, decomposes into a limiting mixed Hodge structure. So in particular, I have a mixed Hodge structure with weight filtration W, and it's polarized by some nilpotent cone. There's a subtle issue here, which is that the Hodge filtration is not well defined. It's actually, it depends on the choice of coordinates, but the nilpotent orbit itself is well defined. And so what that means is that I get this blue map at the top. Sorry, well, it is at the top, at the bottom of the page. Okay, I get this light blue map, and I don't want to say a great deal about what's going on here, but basically this D sub I is a subset of the compact dual that is parameterizing the Hodge filtrations with the property that this is a polarized mixed Hodge structure. Okay. And again, there's some monodromy running around, and I have to quotient out by the by this exponential because of that well-definedness issue. So nonetheless, because I'm dealing with a mixed Hodge structure, I have on the weight graded quotient an induced polarized pure Hodge structure. And that is well-defined, independent of the issue here. And so that gives me a period map on strata. Okay. This thing here you can think of as a period domain, but if we're being strictly honest, it's a Mumford-Tate domain. Okay, so we've got this kind of funky mess, but we passed out to the weight graded quotient, and now we have a nice period map on the strata. So the first statement is that these strata-wise period maps actually patch together to give a proper extension of the period map over B. This is a topological construction. And it's a non-trivial statement. It relies on the several variable SL2 orbit theorem, or if you like, it's taking advantage of the relative weight filtration property. But you can patch these together to get a proper map. And that gives me at least a topological compactification of the image of the period map, basically by attaching the images of the period maps on lower dimensional strata. So naturally, what we were trying to do was to generalize the Satake Baily Borel construction. And for this, we needed one approach was to understand what would be your space of analytic functions on this topological space, which is stratified by quasi-projective varieties. So this raised the question of what can we say about the global geometry of a phi naught fiber. This is going to be some compact subvariety of B bar. And we wanted to understand them better. This is not information you can get out of the local coordinate analysis that you get from the nilpotent orbit theorem. Okay, so let's take a connected component of one of those fibers. And I want to point out that because I've patched things together, it's not necessarily the case that this component sits inside one of these strata. It may cross strata. So in particular, we're going to need to understand how the period map degenerates across strata and how these maps all patch together. Okay, we cannot work strata-wise. Okay, so this page is a bit of a mess, but let me tell you what it says. Okay, it says that if you take this connected component of the finite fiber, it admits a neighborhood with a good neighborhood with a period matrix representation. So in particular, the extended period map is still proper. I have a period matrix representation, and the monodromy over the punctured neighborhood is such that you can show that the determinant of the extended Hodge bundles are trivial over this neighborhood. So the argument goes pretty much, the argument for 3, I just want to mention briefly, it goes pretty much as Deligne's argument goes when he shows that that the Hodge bundles extend across punctures, extend to the normal crossing divisor at infinity. He does this by showing that the Hodge bundles are locally trivial in Schmidt's coordinate neighborhoods. Well, we don't have that anymore, but the determinant is locally trivial. Okay. Okay, so the key observation that goes into this that's new on top of things like the nilpotent orbit theorems is that this proper extension I just defined is closely related to what you would call the reduced period limit or the naive period limit. So what I could do is just associate to my point B at infinity the limit of the nilpotent orbit, which is this F infinity, and would necessarily lie in the boundary of D. So you can show that this defines what we'll call the reduced period limit map from the strata. This is the topological boundary of D. You can further restrict it and actually show it's an orbit. So this is a nice quotient. And the infinitesimal period relation, the IPR, implies that the period map along the strata actually factors through the reduced period limit with finite fibers. And this you can use to show that, that the monodromy over the punctured neighborhood preserves the following Schubert cell. So it's kind of funny, but what I need to do is take the reduced period limit at infinity, take its complex conjugate. And if you remember, Schubert cells are cut out by degeneracy conditions on intersections. And this is the open Schubert cell. So the degeneracy condition is the generic one, which just means that this dimension is the minimal possible. It's the subspaces in the Hodge filtration are as transverse to F bar infinity as they can be. Okay. So it would be nice if we're done because we have a period matrix representation and you'd like to know if we could extract those functions F that we're after from that period matrix representation. In this case, we cannot. The monodromy is too complicated. The entries in the period matrix representation are multi-valued, as they will always be, but they're much harder to get a grip on. We can't just take an exponential to kill off a log term. So what we're going to do is pass to a smaller neighborhood, and we get to that smaller neighborhood by looking at level 1 extension data for the limiting mixed Hodge structure. So remember that from that we have this kind of large funky period map that associates to points at infinity, the limiting mixed Hodge structure. and we pass to the weight graded quotient to get a period map. So we can be a little less forgetful and quotient out not all of the extension data, but remember the level 1 extension data. That is still well-defined, independent of the nilpotent orbit, because this nilpotent cone lies in level 2 extension data, which we're throwing out. And the fibers of this map are nice. They're complex tori, parameterizing the level 1 extension data, which is this direct sum here. So we're being slightly less forgetful. Okay. So again, this new, not quite period map, but the map that retains, that knows about the period map and some of the extension data. These also patch together to give a proper extension, proper topological extension of the period map, through which the first extension factors. So we have a picture, something like the following. Our original period map, our first extension, and then our second extension. So now take this is a proper map. So a connected component of a fiber is compact. It'll sit inside the fiber of finite. And this fiber admits a good neighborhood, or an even better neighborhood. So again, the extended period map phi1 is proper, which we're going to need for Grauert. The Hodge filtrations themselves are in fact trivial over the neighborhood. And here I am taking advantage of neat for that argument. And the period map has a matrix representation over the punctured neighborhood. And this is a very nice period matrix representation. It's almost as good as what we have locally from Schmidt's nilpotent orbit theorem, which is absolutely remarkable. And in particular, what you can show is that the horizontal matrix entries are of the following two types. So let me clarify real quick. I've moved out of the classical setting. I now have this non-trivial infinitesimal period relation. And that means that the full period matrix representation is determined by a subset of the matrix. And I'm calling those the horizontal components. Those are if I understand those, I understand the full period matrix up to constants of integration. Okay. So as you saw in the local case, those matrix entries are going to be of two types. They're either holomorphic and well-defined, or if I choose my coordinates appropriately, the exponential is well-defined. Okay. And this gives the functions epsilon mu tau nu from O bar 1 into CM to apply Grauert's argument. So let me give you another example of what these look like in a non-classical case, just so you have something to hold in your hand. So let's look at the simplest non-Hermitian case we have, which is weight 2 and Hodge numbers 2b2. I think for this example, you should probably take B to be at least 4. So the period map is given just by the first subspace in the Hodge filtration by Hodge-Riemann 1. And so I'll just describe a matrix representation for F2. It's two-dimensional, so it's spanned by two vectors. It's these two column vectors. The horizontal part is this middle piece. These entries down here are determined up to constants of integration by those above. And most of these turn out to be holomorphic, but there's one part that's multi-valued, and we can make holomorphic and well-defined by taking an exponential. So in this case, the map F that's used looks like the following. And maybe just for a little more information, the period map itself on the strata is given by the blue entries. They're the weight 0 entries. And the one that also keeps track of the level 1 extension data is given by the green entries. Those have weight graded degree -1. And I am so sorry, I completely misjudged how long the talk would take. That's actually what I have to say, but I would be happy to answer questions.
Let's first thank Colleen for the talk. Thank you very much. So are there any questions or requests for further elucidation or comments? Dan?
Oh, I didn't say anything about the connection to the toroidal construction. I should do that at some point.
That would be one question, but another question is how far does Baker, Brunebarb, Zimmerman give you, and where? I mean, I wasn't clear about how things are tied together.
Yeah, so the BBT result tells you that the image of a period map is quasi-projective. So it's a beautiful statement over the base B, but it doesn't tell you anything at all about what happens as you degenerate across strata. And this is because they show the image as quasi-projective by showing that the Hodge line bundle is free, base point free over B. And they do this with sections that vanish at infinity. So there's no information at infinity from their approach. If you wanted to use that kind of, those kind of ideas to say something about extensions, you'd basically need to show that the Hodge line bundle is free over B bar. And that means you need to understand the degenerations.
But I mean, for example, is there such a thing as a Hodge line bundle over B bar?
Yes. So the Hodge filtrations, the Hodge vector bundles extend. You can take their determinant and then the product, and that's the extended Hodge line bundle.
So you're saying a posteriori you can extend. After your result, you can extend.
No. That's Deligne. Deligne's extension of Deligne's canonical extension of the Hodge bundles.
But in order to extend, you need to know what to extend over, right?
But I have B bar. That's part of my input. And that's really important, that I already have this structure at infinity.
Okay, so, okay.
Well, I think we may be waiting for other people's questions, but can I just ask one thing, which is there some point at which the construction depends or doesn't depend on the B bar that you started with?
Yes, I mean, absolutely. It depends on the B bar that I started with, because I'm building the compactification out of the limiting mixed Hodge structures at infinity. So I am using the normal crossing divisor at infinity.
But shouldn't those be at least somewhat independent? I mean, if you sort of choose any curve, shouldn't it have a limiting mixed Hodge structure, which would be one of those, basically? I mean, you could check. I mean, let's suppose we're fixed B, right? But not necessarily the compactification B bar.
Sure. Yeah, I could get.
You look at like all the possible limiting Hodge structures you get along all possible analytic curves inside B or something like that.
Yes, but that sounds like a lot to control.
Yeah, I don't know whether it would make sense to. I mean, so you're sort of working stratum by stratum on the compactification B bar.
That's right. Yeah.
But shouldn't you conjecture some other that at least vaguely it's independent? I think Dan has a comment here.
For instance, if you blow up your given B bar in a controlled way, well, of course, you can extend through the existing one from B bar, but how does it relate to the extension you construct on the blow up?
Yeah, I agree. This is an interesting question. It's not one that we've thought about. One would expect there's a relationship, but I decline to comment publicly.
So you think there might be examples where it's not the same, basically?
I mean, you would sort of expect that if you blow up, the extended period map will just collapse what you blew up. I mean, that's my naive guess.
Right. Well, that would say that it's independent of the extension.
Right.
It would, if that is correct.
I mean, would there be
but the argument really uses having this compactification. It gives us a sort of finiteness and control.
How about we call this the Robles-Simpson conjecture? And so you are not
Robles, I don't know. Abramovich.
I think in partial answer to the question is, let's suppose for the sake of argument that the phi upper T is 1-to-1. And what would be an ample line bundle? It's, in the toroidal case, it's like, what are the ample line bundles on the various toroidal completions? So, I mean, we can say some things about that, but it's rather subtle. So, for example, suppose we just take the first interesting case where the dimension of B is 2. Suppose your Z then is a configuration of curves, and the Satake, Baily, Borel map contracts those curves to a point. So the intersection matrix is negative definite. What is an ample line bundle up on B described Hodge theoretically? Well, it's not just a linear combination of the Hodge line bundle pulled back from Satake, Baily, Borel, plus the curves Zi that are contracted with certain coefficients. Those coefficients have Hodge theoretic meaning in terms of Chern classes of the Hodge bundles. And we don't know exactly what those should be. There's a Hodge index type phenomenon going through. In dimension B equals 2, you can say what it is, but in higher dimensions, we don't know what it is. So, I think that's an incomplete answer to the question, but it I think is a rather subtle one. The P bar, P upper hat, should be projective. That what is an ample line bundle on it? It's got to be constructed Hodge theoretically. The only Hodge theoretic information you have are the Hodge bundles, and we can take determinants of them with various coefficients. So conjecturally, that's where you get your ample line bundle, but we don't know how the combinatorics of how those coefficients should be constructed, what they should be. We're really looking, it's a Hodge index, it's a Hodge index type phenomenon going along in higher dimensions that so far we just don't understand.
I have one more question. Maybe you said it and I missed it, but your compactification in the peer domain, what do you think will it just parameterize the weighted pieces of the Hodge structure, or will it also parameterize some extension data?
So the, where did it go? The one constructed here, the bottom one, that's just going to parameterize the Hodge structure on the weight graded pieces. So what's going on is that we have this completion that I was discussing today. This encodes all the limiting mixed Hodge, all the data in the limiting mixed Hodge structure. So in particular, the full mixed Hodge structure modulo the ambiguity in the nilpotent orbit. and it will surject onto what I was calling P bar, which is essentially the generalization of Satake, Baily, Borel. So this one we have with Radu topologically, but the problem has been to show that it has an analytic structure.
And
In which case the Hodge line bundle will be ample.
Sorry, probably I missed the whole point of the talk, but so the upper one, which contains every information, you have this, I mean, this exists with an analytic structure?
Yes, it's Moishezon. It's an algebraic space.
And you have the factorization over this, or
oh, this map?
Was that the problem? I mean, for the extension to B bar, does this always factor over
this map here?
No, the when you add the B into the picture.
Ah, right. So so the picture is that I have some period map phi.
Yeah.
Because of the way we're using the IPR and the argument, I need to work with a map that has connected fibers. So we are taking the Stein factorization to get that map with connected fibers. And what we have is this extension. So this is a finite cover of the image of the period map. Of course, what we really like to do is to get an extension of phi. But we haven't quite managed to do that. What we've managed to do is get it up to finite data. And that extension is essentially encoding all the information in the limiting mixed Hodge structures at infinity. So it really does have the flavor of the AMRT toroidal construction, or what you'd expect from Kato and Usi, if you had a fan.
Okay.
I guess we sort of think of it as a relative toroidal completion. You give the initial data, and what it produces is a toroidal-like object that's the maximal, has the maximal amount of Hodge theoretic information that's retained in the completion.
Okay, thanks.
Are there any further questions? I guess, I mean, I'm not sure. I could just ask another one, but a little bit related to what Philip said, maybe. But I'm not sure if this makes sense or not. But is there some kind of horizontal distribution on the kind of bigger period domain where you add in the information of the graded pieces of mixed Hodge structures? That's sort of taking period domain and adding points which correspond to mixed Hodge structures up to some equivalence relation, right?
So if you look just at what's happening, so if we look at just the map here that's given by the limiting mixed Hodge structure at infinity, it comes out of Schmidt's nilpotent orbit theorem. This is a subset of the compact dual, just like the period domain. It's not a period domain, but it is a homogeneous subset of the compact dual. And the lifted map does satisfy the infinitesimal period relation there. That is in the background everywhere.
But you're sort of gluing that piece onto the bigger piece, onto the main period.
No, I'm not gluing this.
You're not gluing that. I mean, there must be a way in which you're gluing that thing onto the other. And the question would be, is there some compatibility with those?
You know, I think that if I try to explain it in terms of attaching this, all of a sudden I'm going to have to start worrying about how this nilpotent cone transforms under the global monodromy. And then I have fan issues. I don't think that, I haven't found it productive to think about the problem from that framework. This thinking about it as a quotient by a proper holomorphic equivalence relation, coupled with these kind of global results at infinity on period matrix representations, is how this thing is built. We're really not attaching,
so you're
explicitly
not really,
that I can see, we're not attaching predefined boundary components. This is really a different approach.
Space in which the whole thing maps to, basically. you're sort of not getting like a big space to which the whole big
Yeah,
period.
That's
space.
right. There's no ambient construction.
Okay. Which might be structurally, I guess, I don't know. Maybe there's no way.
I wonder if I can ask so you extended over the Stein factorization. So I wonder if you're willing to say what the difficulty to descend. I mean, is it just extending over codimension 1 loci and then it would dogs or something like?
So this picture here captures fairly well what's the problem with the extension. I have a lot of control over the horizontal component of the period matrix. The entries are either holomorphic or I can force them to be holomorphic after taking an exponential. So this exponential here seems to be playing structurally a role similar to that of the monomials in the toroidal constructions. The problem is, to get rid of this finite data issue, I have to deal with the whole period matrix. And the monodromy action here is more complicated. And I can't just take exponentials to force something that's multi-valued to be holomorphic. It's very interesting. I don't know how to deal with it. It's genuinely non-classical phenomena. Everything's horizontal in the classical case. But in the non-classical case, if you want to get away with this finite data issue, we have to figure out how to deal with these multi-valued functions.
Can you deal with them over a curve?
I don't see that helps.
Okay, so that was my question, basically.
Okay, any further questions from anybody? We still have plenty of time. Okay, so let's thank let's thank Colleen again for a nice talk.
Thank you.
Okay, so I guess we'll wrap this up. So the next talk is at 1:30 p.m. Miami time.